Assalamu alaikum. Welcome to the new lecture. So today, in the last lecture, we have discussed about the testing of the transformer. We'll continue with the testing of the transformer. So today we'll discuss the subnerves back-to-back test. So earlier we actually did the two tests, that is the short circuit test and open circuit test. So, but we did not conduct them simultaneously. We conduct them separately. But sometimes, uh, but in usual practice, that in the transformer is used, the two losses are occurring in the transformer simultaneously. In open circuit test, we have only the core loss present, and in short circuit test, we have only the copper loss. So the heating will be less in both the tests. What I mean to say is that. So here, in subnerves test, this has been taken into consideration that both the losses are taking place in the transformer simultaneously. So the heating of the transformer is because due to heating there may be some change in the resistance or any other thing, any other parameters. And so whatever the value we get, that will be the exact value. So while open circuit test and short circuit test on a transformer yields its equivalent circuit parameters, these cannot be used for the heat run. That means heat will not be exactly equal when the transformer is actually present in the you can say in the ground. So heat run test, wherein the purpose is to determine the steady temperature rise if the transformer was fully loaded continuously. Because in practice it will be fully loaded, will be having both the losses simultaneously. This is so because under each of these tests, that is short circuit test and open circuit test, power loss to which the transformer is subject is either the core loss, that means in case of this open circuit test, or copper losses, that is in case of short circuit test, but not both. It will not be both present. The way out of this but without conducting an actual load test is the submerged test. In this case, we're not actually loading the test by putting some load, but the submerged test is an indirect test of this where both the losses are present in the transformer, but we are not actually loading the transformers, which can only be conducted simultaneously. But here we need to have two identical transformers on which this submerged back-to-back test can be performed. In conducting the submerged test, the primaries of the two transformers are connected in parallel, while the secondaries of the two transformers are connected in phase opposition and in series. And the primaries are connected in parallel across the supply voltage V1. That means V1, that is, this voltage will be given on the low voltage side. You can see from this figure, these are two transformers, two identical transformers. One is this, another is this. These two are this is the primary of this transformer, this is the primary of this transformer. They are connected parallel. You can see over here, they are connected in parallel. And these two transformers, they are connected in series but in phase opposition. That means if we have dot here, here also should be dot. So the net voltage across this loop will be equal to 0. So this can be determined by either doing the polarity test, or if you don't do the polarity test, you can simply put a voltmeter over here and see the voltage across it by applying this voltage over here. So in that case, if this V2 is close to 0, that means the polarity, they are connected exactly the proper manner. If the voltage that is measured by this voltmeter is the double the rated voltage, that means they are connected in the phase opposition. So we need to avoid this and we need to change the connection. That means we have to connect this T1 to T4 and this T2 to T3 in that case. So we'll assume here the polarity are same and we have the connections that we have done are the proper connection. But in practice, we have to be very sure and we need to use this voltmeter for that surety. For the secondaries to be in phase opposition, the voltmeter, this T1 must be 0. That is what I have just told you. Otherwise, it will be double rated voltage, in which case the polarity of one of the secondary must be reversed. Current and low voltage V2 is injected into the secondary circuit of T2 and T4. We'll keep the voltmeter as it is. Then we use this circuit, ammeter, a wattmeter, and a low voltage supply over here to inject the current in the secondaries of the transformers. Supply 1 and supply 2 are of the same main. They are taken from the same mains. You can connect it over here. You can, but this has to be supplied to this through the variac, so that we have to supply some less voltage, because this is very similar to the short circuit test. You will see it will be exactly same as that of the short circuit test. As per the superposition theorem, if V2 sources should assume short circuit, because when we suppress this voltage source, it will be a short circuit over here. You can see we'll be having a transformer, two transformer primaries connected in parallel, and they have been supplied a voltage of rated voltage on low voltage side, and these two secondaries are connected in parallel because this will be short circuited. Now, since they are connected in phase opposition, there will be no current flowing through the secondary. This condition is as if it is identical to that of the no load current, because here we are giving rated voltage, the secondary has no load current, the secondary has no current, and only the primaries have the exciting current or no load current. But here, since there are two primaries, the current that is supplied from this source will be equal to twice I0. One I0 will flow through this, that is shown in this diagram. That is this shown in red. Why not I0 is flowing through this, and why one I0 is flowing through this. The two transformers have been open circuit to the source V1, as the secondaries are in phase opposition, and therefore no current can flow in them, that is in the secondary. The current drawn from the source 1 is thus twice I0, twice the no load current, that is this, and the power that is drawn from this will be equal to twice P0, that is the core loss of the two transformers, that will be equal to twice Pi, twice the core loss of each transformer. When the AC supply 1 is short circuited and we are calculating the effect of this voltage, the transformers are in series connected across V2. This V2 will be applied to the series connection of this secondary and this secondary, and are short circuited on the side of the primary. Here, since it is short circuit, you will see that it will be short circuit on this, but there is slight we can say, when this happens, you will see that the current that flows from here, that is full load current, when we apply the voltage at this point and we increase the voltage in such a way so that the full load current flows in the secondary of the transformer, because you will see that this is the high voltage side, and in case of a short circuit test, we supply the voltage from the high voltage side and short circuit the low voltage side, and you can see low voltage side will be short circuited through this supply. But in this case, the current flow will not be through this. The current flow from here will be the current flowing, the I full load current is flowing in this direction, and due to its opposition, the IFL1 will be flowing through this direction. Okay, and then for this case, since the current is flowing opposed to this direction, here the current will flow upwards. It will not follow this path, that is, the current will not flow through this path. Actually, it will circulate in this winding, primary winding circuit, like this. So in that case, there will be no burden of this primary current, that is the counterbalancing current of this secondary current from the supply. It will circulate in this. So that means the current that is supplied by this will always be twice I0. It will not be some twice I0 which is affected by this IFL. So from here it will always be IFL. So I hope you understood this. This will circulate in this, the full load current, counterbalancing full load current. So, and it will appear as if it is short circuited because the supply will be short circuited over here. So that means this is equivalent, this circuit, parallel circuit, is equivalent to the open circuit test of the transformer, and this circuit which is equivalent to the short circuit test of the transformer. In this case, the current drawn by this will be twice I0 as compared to the earlier open circuit test. So the wattage, that is W1, it will be twice PC. Similarly, for this case, IFL will be same as IFL because it is series circuit. It will not be different from this, but this voltage that is supplied to this will be equal to this VSC by 2, actual voltage by 2. That is, it will appear across this, and then yes, W2 will be also twice that of the copper losses in this winding and in this winding. So in that case also, this W2 has to be taken care of. Therefore, the impedance seen by the V2 is twice R2, and when V2 is adjusted to circulate the full load current, the power fed to the circuit is twice PC, that's twice the full load copper loss of each transformer. Thus, in Softness test, while the transformers are not supplying any load, full iron loss occurs in their cores and full copper loss occurs in their winding. Therefore, net power to the transformer being twice P naught plus twice Pc, that is only the losses. The heat run test could therefore be conducted on true transformer while only supplying the losses, not the actual loading. So calculating the parallel parameters, y naught is equal to Gi minus B JBM, y naught is equal to I naught by V1, while definitely I naught will be the half of this current measured by this ammeter. So you need to take care of that. So this will be similar. V1 square Gi will be equal to P naught, where P naught is equal to W1 by 2, that is measured by this wattmeter. So then Gi is equal to P naught by Vi square, Vm is equal to root of Y naught square minus Gi square. For series calculation, Z is equal to VSC by ISC, ISC will be equal to IFL, and VSC will be equal to V2 divided by 2, that is V2, which is measured by this voltmeter. Okay. So finally, R is equal to PSC divided by ISC square, while PSC is equal to W2 by T, that is the major power here. It has to be halved. Then X will be equal to root of Z square minus R square. So this is how the Softness Vector test is done. It gives us the simultaneous losses in the transformer, which is we can say which is done on the two identical transformers. Now, before going into the voltage regulation and into the efficiency, we'll first discuss about the per unit system, because this per unit system will be using in discussing the different topics, because these topics will be quite easy while dealing with this per unit. So what is this per unit system? Usually, while carrying out the analysis of electrical machines machine system, it is usual to express the voltage, current, this volt ampere, that is kVA or power or reactive power or apparent power, and impedance in per unit. All these quantities are expressed in per unit or percentage. So of the base of or reference values of these quantities, we actually want them to convert into per unit with respect to some base. So the per unit value of any quantity is defined as a ratio of the actual value in any units, the base or reference values in the same units. And you can see from here the per unit value will be unitless. While the base values can be selected arbitrarily, it can be selected arbitrarily, but it is normal to choose the rated values of the devices, its base values. So for transformer, its base values are selected as its kVA base, VA base or MVA base, and it is voltage rating. There are obvious advantages of this per unit system. What are these advantages? There are mainly two important advantages that occur from the use of per unit system. The first one is that the parameters of the transformers, as well as any rotating machine, as well as any electrical machine system, lie roughly in the same range. We can say numerical value or a narrow range. You will see that we say that the voltage regulation of a good system should not be greater than plus minus 5%. So in per unit, we can say that the voltage may vary from 0.95 to 1.05 per unit. So this is how the range varies. It only varies from 0.95 to 1.05. Same is the case with power. Same is the case with, you can say, impedance or current. They will not vary too much. You will always see that the full load current can be expressed as 1 per unit, and if there is a fault, we can say that when there is fault or short circuit, that current may be three times this full load current. We can say 3 per unit, 5 per unit, 10 per unit. Still it will be, we can say, a narrow range. So that is one of the advantages of the per unit system. The second most important advantage of the per unit system is that it is most convenient in power systems, as it relieves the analyst of the need to refer circuit quantities to one or other side of the transformer. So while dealing with the transformer, you will see that we try to refer it from the towards the primary side or the secondary side. But in case when we do the per unit system, the referring case goes, we don't need to refer the transformer whether primary or secondary, because whether we are referring it to primary or secondary, it will remain the same. The value of the impedances of the transformer will remain the same. That is the beauty of this per unit system. So it is usual practice to use the per unit system for modeling real-life large integrated power systems and in computer simulation of machine system for the transient and dynamic analysis, because of its obvious advantages. So base values of various quantities are related to each other by the usual electrical laws. For a single phase system, P base Q base or VA base will be related by V base into I base. Actually, this should be the value of this VA base. Then Q base and P base will be definitely multiplied by their power factor to get the P base, and Q base it will be also multiplied by power factor. Sorry, not power factor, sine of theta. So R base, X base, Z base will be calculated V base by I base. So G base, P base, and Y base, I base by uh, V base. First, we need to calculate. We need to first select two base quantities, and from these two base quantities, other two base quantities, other base quantities can be calculated. For example, as I have told you that we need to express voltage, current, VA, and impedance in per unit. So first, usually VA and voltage are taken to be the base values, and then current base value and impedance base value are calculated from these values. So it's always a practice to select this VA, kVA, or MVA base for higher rating transformers or higher voltage machines as a base, and then V or kV base are first selected for voltage base, and their choice automatically fixes the other base values as per the above equations. For example, if we have to, since kV base is fixed, we can calculate the and this base is fixed, we can calculate the I base, that is equal to VA base divided by I base. Similarly, then we can calculate the Z base. Z base will be equal to V base by I base, and I base is equal to Q base divided by uh, I base will be equal to Q base divided by V base. So overall this will be equal to this Z base will be equal to V base square divided by VA base. So in that way we can calculate all these quantities. Now then Z per unit will be equal to the actual value of the impedance multiplied by or divided by the Z base. Z base will be equal to, what is Z base equal to? V base square divided by VA in base. So that is this value. In large devices and systems, it is more practical to express the bases in kVA or MVA, as I have told you earlier, and voltage base in kV. Then the above equation is written as, if the voltage base in kV and if the VA base is in kVA and this is in kilovolt, then the Z per unit will be defined by this, because here it is only 10 to the power 3, here it is 10 to the power 6. So when you use the kVA directly value, you have to incorporate it's 1000, because this k, when it's square, it is 10 to the power 6, this is 10 to the power 3, there remains 10 to the power 3, that is what here 10 to the power 3 remains. Similarly, for this case, when we use the MVA base, 10 to the power 6 here for this, and k square, that is 10 to the power 6, they will cancel out. You can use directly without using any multiplying factor. So when MVA base and k base are modified, the new impedance is given by, that means Z per unit for new base will be changed. It will not remain the same for different bases. If we change the bases, you can see, if we change the base, Z base will change automatically. This Z per unit will, because this will be constant, this will change. So in that case, let us say Z per unit for MVA base is like this. So Z per unit new will be Z ohm. It will remain the same. It will not change. This will change. MVA base new, kV base new. That old was, this will remain the same. This is MVA base old, kilovolt base old. So divide this by this, it will be equal to Z per unit new divided by Z per unit old. It will be MVA base new divided by MVA base old, multiplied by, it will come up kV base old, kV base square old divided by kV base square new. So when we take this Z per unit old to this side, it will be this equation. So this is how, when we change the base of the Z per unit into one value to another value, this Z per unit will change from older value to newer value. So these equation will help to transfer the one per unit into another per unit. Now let us try to do this numerically. You will see that what will be the effect. The exciting current was found to be 3 ampere when measured on the low voltage side of a 20 kVA 2200 volt transformer. It is equivalent impedance referred to high voltage side. This is referred to high voltage side impedance 8.2 plus J 10.2. Choose the transformer rating as its base. Find the exciting current in per unit on the low voltage as well as the high voltage side. Express the equivalent impedance in per unit on the low voltage as well as the high voltage side. Before going to do this numerical, the important thing that I thought I forgot to tell you, that when this happens, in this case, the base value of the voltage changes from from primary to second, or we can say, if we have two voltage, we know that primary has one voltage rating and secondary has one voltage rating. So when you go from the primary and secondary voltage, if we have chosen the rated voltage as the primary voltage, base value, sorry, as the primary voltage, and when you go to the secondary, the base value has to be changed as the secondary voltage. So this is the only thing that you need to keep it in your mind while doing this experiment. So V base high voltage, let's assume this will be 2000, because we'll first fix the values of the kVA base. kVA base will be 20 kVA, and voltage base will be 2000 on the high voltage side, and voltage base on the low voltage side has to be 200 volt. That is what I have just told you, that this base changes from primary to secondary, or low voltage to high voltage. For high voltage side it will be 2000 V base, and for low voltage side V base will be 200 volt, and this kVA will be same throughout the transformer. Now V will be equal to 2000. Now we can calculate the I base on high voltage side by dividing 2000 to this kVA. That is 20,000 divided by 2000 will be equal to 10 amperes. That will be equal to 10 amperes. Similarly, this base voltage on the low voltage side will be 200. So base current on the low voltage side will be 2000. 20,000 divided by 200, that will be 100 amperes. So these are all calculated. Now we can calculate the high voltage base impedance and low voltage base impedance. So high voltage base impedance will be equal to, we can say, VB divided by IB, or it can be equal to, or you can directly calculate it from this equation. That is VB square by this VA. It will again be same, there will be no difference. That is 200. 2000 divided by 10, that is 200 ohms. You can calculate it from this also. It will be equal to V square, that is 20 square, that is 4 into 10 raised to 6 divided by 2 into 10 to the power 4. It will be again equal to 200. So base impedance on the low voltage side will be equal to 200 divided by 100. That will be 2. So it is given that the exciting current when measured from the low voltage side is 3 amperes. So it is per unit value will be equal to, you have to divide it by base value on the low voltage side of the transformer, that is this value. So it is divided by the base value of the low voltage side, it will be equal to per unit, 0.03. The exciting current referred to high voltage side, when you refer this to high voltage side exciting current, so it has to be divided by 10, because it will be reflected to the other side of the transformer by inverse of the voltage, this voltage ratio. Yes. So when it is referred to the secondary side, sorry, primary high voltage side, so this current will be equal to 0.3. So I naught high voltage side then will be equal to, in per unit will be equal to 0.3, that is the actual value, divided by its base value. Base value will be 10 amperes. So when you divide by 10 amperes, it will be 0.03. So exciting current, you can see on both the bases will have the same value. So Z on high voltage per unit will be equal to, because here the Z is given on the high voltage with respect to high voltage side, so it will be this. So we can directly divide it by the Z base on high voltage, so we'll get, so 8.2 plus 10 plus J 10.2 divided by 200, it is equal to 0.041 plus J 0.051. This is the per unit value of the Z, or the impedance of the transformer when we use the high voltage quantities. On low voltage side, you will see that this will be first transformer, this will be first referred to the low voltage side, so you have to divide it by 100, that is 10 square, it will be 0.082 plus J 0.102. So it will like this. Then converting it to the base, this per unit value, we have to divide it by the Z base in low voltage, that is 2 ohm. So when you divide by 2 ohm, it comes out to be 0.041 plus J 0.05. You will see that these two are almost identical. So the earlier remark is therefore confirm that the per unit value is referred to either side of the transformer are the same, so long as voltage bases on the two sides are in the ratio of the transformer. So usually we this is usually case. What does this mean? That means we change the voltage basis as per the transformer ratio. So on high voltage side, it will be the high voltage rating of the transformer. On low voltage, it is the low voltage rating of the transformer. So this was about the per unit system. We'll be using it quite often. So I hope you will do 2 or 3 numericals on this. This numerical was just to show you that why it eliminates referring of the transformer when we could do the system. Now we'll discuss voltage regulation and efficiency. We'll first define the efficiency. So the rated capacity of a transformer is defined as the product of rated voltage and the full load current. That is, V rated and the full load current on the output side. And we know that the rating is the kV. I have discussed that in the earlier classes. The power output depends on the power factor of the load. The power output means the real power. It depends upon the output power. The efficiency neta of a transformer is defined as the ratio of useful or real power output to the input power. Thus, this efficiency is divided by output power divided by input power. Usually, the efficiency of a good design transformer is around 96 to 99%. It is of no use of determining by measuring the output and input under the loading condition because the wattmeter readings are liable to have an error of 1 to 2%. There are actually two reasons why don't we do this, because as I told you in the lab also, when we calculate the efficiency, we can do the directly, calculate the output at the full load, and at the same time we can calculate at the input. So we can directly take the ratio of this output by input, we can get the efficiency. For the lower rating transformer, it is quite easy to find that such load as 1 kV, 2 kV, or even 5 kV. But for higher rated transformer, which may be of the order of 100 kVA, 500 kVA, 1 MVA, or 50 MVA, the loading may not be present. So it is required that we should try to derive on some indirect formula to calculate the efficiency. And also, because of the non-reliable reading given by the wattmeters, it may result in the error that is 1 to 2%. Now, the best and accurate method of determining the efficiency would be to find the losses from the open circuit and the short circuit test. So this also I have shown it in the lab. So with the data, that is the data efficiency can be calculated as that is output divided by output plus losses, because output plus loss will be equal to input. Or you can take it like this: 1 minus losses divided by output plus losses. You can take it to this side, it will be equal to output plus losses minus losses divided by output plus losses. It will be again this equation. So in the above equation, the effect of meter reading is confined to losses only. Here we need to only calculate the losses. We're not dependent upon any other things. So the overall efficiency obtained from it is far more accurate. It may be more accurate as compared to where we calculate the output power to the input power. Various losses in the transformer have already been discussed. That is the two important losses: iron losses or copper losses, iron loss and copper losses, that are shown in this figure. It's a transformer, it is fully loaded. We have iron loss in the core and we have the copper losses in the winding. So this is how the transformer can be modeled. So we have input, we will be subtracting the two losses, and then the remaining of the real power will go to the load. Now, effect of the load and load power factor. We'll see what will be the effect. The iron or core losses depend upon the flux density and so on the induced EMF. As V1 and E1 are equal for all loads, practically for all loads, there will be very negligible difference. The losses can be regarded as constant. That means the iron loss can be regarded as constant independent of load for a constant primary voltage. But the copper losses in the two windings are PC is equal to this, the copper losses, I1 square R1, that is the primary, and this is the secondary. Let us take them this, refer to the secondary side, it will be equal to I2 because this I1 will be equal to this I2 dash. In that case, this can be taken to this side, and this is I2 square into R equivalent 2. While R equivalent 2 is the equivalent resistance, therefore to the secondary side. Thus, it is found that the copper loss vary as the square of the load current. So transformer output can be calculated in terms of the current voltage and power factor is V2 I2 cos of theta 2, and theta 2 is the load power factor. So neta, that is the efficiency, will be P naught, that is V2 I2 cos of theta 2 divided by V2 I2 cos of theta 2 plus Pi plus I square to R equivalent 2. So this is the equation of the efficiency. Now, where V2 is the rated voltage, if V2 varies slightly with the load, but usually this V2 varies slightly with the load, but the variation is so small, 3 to 5%, that it can be neglected for computing efficiency. We can calculate and we can say this is constant. The above equation shows for that the given power factor efficiency varies with the load current. It can be written as, while here we have divided I2 in the numerator as the denominator. This I2 and this I2 will cancel out. Here I2 will be divided. Here one I2 goes. So now we'll calculate the maximum efficiency. For maximum value of efficiency for a given theta 2, we'll keep this constant. The denominator of the above equation must have the least value. This will have the least value. We can do it in the normal way. It will also give us the same value, but we'll do it only for this case. So the 2 or 3 steps will be can say neglected or can say eliminated. The condition for maximum efficiency obtained by differentiating the denominator and equating to 0. So when we differentiate this equation, this is constant, this goes, its integration, sorry, differentiation with respect to I2 will be equal to minus pi by I2 square, because pi is constant, and its differentiation will be equal to R equivalent 2. So when we equate to 0, it comes out to be that I2 square R equivalent will be equal to pi. So I2 square R equivalent to is equal to pi. That is copper loss which are variable is equal to core loss which are constant. That means that the efficiency is maximum at the load when the copper losses, that are variable losses, are equal to the constant losses, that is the core losses. So this is the condition for the maximum efficiency. So I will continue with this in the next class. For the time being, I will stop over here. Thank you.